Hi, everybody. Looks like we got a lot of people here. That's great. So I guess, yeah, welcome to the live stream on Gravity. Let's see if we can have some fun today. All right. Minimize that. Hopefully my audio is good. Looks pretty good on my end. All right. Looks like we got a busy chat, which is great news. So, this is going to be, a pretty standard live Q&A. I'm going to be taking questions from the chat as much as I can. Hopefully it's not too much of a madhouse. And we'll see if we can, address some of your concerns, answer some of your questions, and I think it'll be a good time. So on that note, first of all, yeah, NASA shirt. Can you actually, I don't know if you can actually see that. I think we're good. All right. So let's see here. I don't know how many of you have seen my general relativity playlist, but I think I'll just assume you basically haven't seen anything, and we'll see where this takes us. All right. So first of all, just to get some clarity here, right? We are going to be sticking to gravity as it is described in general relativity. That's Einstein's version of gravity that was published in 1915. Now I say Einstein, but it was also Einstein and Hilbert and Grossman, and there was a whole bunch of other people that worked on it. It wasn't just one person, but the big names are definitely Einstein and Hilbert. They published a lot of the same papers around the same time in, 1915-ish throughout the year. So it was a collaborative type project. And of course, a lot of the things that you are familiar with, black holes and stuff like that came out of it, were not part of the original papers that Einstein and Hilbert published. They were things that came out afterward as other scientists, other physicists got their hands on that stuff. So there may be times today where things get a little mathy, but what I'm going to do is I'm going to be pulling out a few pages from the general relativity chapter in my book. And so you'll have some visual aids as we go. I can screen share during the stream. But I guess first, let's start with some questions. We have one that came in before the stream started by 10 Boxing, and his question was about Science Clicks visuals. Science Click English, I think, is the channel that most people are familiar with. And he put out a video where he had some... they're called geodesics. They're the paths that you take in space-time. And they were pointed, they sort of curved toward the Earth, and the object, the apple, I think, was in the visual, followed it down to the ground. And I've done that in a few of my general relativity videos, some of the older ones especially. Geodesics are a big deal. They are the shortest, or I should say the extremal path between 2 points. They're the things that outside of, other forces like electromagnetism or something, those are the paths that things are going to take. And sometimes those are straight and sometimes those are curved. And that's sort of what general relativity is all about. And 10 Boxing's question was, if you had a planet made of water, would that curve go all the way to the center? And absolutely 100% it would, yes. Now, whether or not an entire planet made of water is possible is a whole other story. But given that situation, given the very unlikely situation, yes, the path would would go all the way down toward the center, and eventually that would stop, and that object would sort of become part of the overall path, the overall geodesic of the Earth or that planet orbiting its star. But while we're talking about geodesics, right, this stuff is all sort of mathematical. And so what I'm going to do is I'm going to screen share real quick. I think I could just do that. Hopefully that works. Woo, infinity. All right. And so what I have here is the general relativity chapter in my book, and geodesics are on, let's see here, 305. All right. So what we have here, I'll zoom in a little bit. Don't freak out about the math. I'm going to be explaining everything as I go. But basically, this is the geodesic equation. Hopefully you can see that. Oh, whoops. I'll pull up the chat here so I can see it and respond to people. But this is the geodesic equation. And essentially, this is half of the story, right? This is one of the two major equations in general relativity. Basically, there's this statement that I think John Archibald Wheeler said one time it said that matter tells space-time how to curve and space-time tells matter how to move. And that is true. And those two halves of that statement are basically the concepts, the overall concepts behind the two major equations in general relativity. That is Einstein's field equation, which we'll get to at some point today, I'm sure, and the geodesic equation, which is, I think this way, this equation up here. And so essentially what this is sort of a version of, this is sort of a generalization of Newton's laws, right? So before Einstein, we had Newton's laws of motion and Newton's law of gravity, and that's sort of how most things worked. And it works pretty well, like 99% of the time. But this equation here is sort of a generalization of that, right? In this case, typically, when you think of Newton's laws, you think of F equals ma. Force is mass times acceleration. It's sort of one of those, like, the major equations in an intro physics class, where you exert a force on a mass, and that causes an acceleration. And that sort of behavior is something that happens in Einstein's model as well. We're still trying to explain motion via things like forces. And so in this particular case, I don't know if you can see my mouse pointer. Yeah, it's there. Okay, so the mouse right here, this term right here looks real fancy. I don't know if you're familiar with calculus, but that's basically the acceleration, that first term. And this 0 over here would be F divided by m, right? So this would basically be, if you didn't have this big term here, we're going to ignore that for a second, you would have A equals F over m. Now, in this case, the way this is typically written, the F is 0. There's no forces acting on the object. So there's no electromagnetism, no strong or weak nuclear forces, none of that stuff. Gravity isn't a force, and so it doesn't get included in the force side. So we get 0. The force is 0, and in Newton's laws, you would expect the acceleration to be 0, but that's not always the case. And so as you can see here, according to the geodesic equation, we have the acceleration term, but we also have this term here. These big fractions, they're not really fractions, but these big fractions are the motion of an object. And then this is a Greek capital gamma, but this is something called a Christoffel symbol, and it has to do with the curvature in, your space-time, as well as like the coordinates you're choosing to represent it. Both things are included in there. And And so this big term here, this term represents the curvature of the space-time. And so what ends up happening is you can end up with an acceleration just because of curvature. You don't actually need a force. And so what general relativity is saying here is that sometimes a force can cause an acceleration. That is true. That carries over from Newton's laws, but also that curvature can cause acceleration. And so general relativity is sort of the realization that not all accelerations are caused by forces, which is kind of wild to think about. But that's essentially what the geodesic equation says. It says that, sometimes forces can cause accelerations, but ultimately, if you don't have any forces, acceleration can still happen. If the space-time is curved, and that usually happens around something, right? Which brings us to Einstein's equation, which I have a little post-it here with all my page numbers. Einstein's equation is 272. And so scroll down a little bit. All right. And so this bad boy is Einstein's equation. And this is sort of the one that everybody knows about, right? And this is the first half of the statement. This tells us how matter, or we should really say energy, curves space-time. Because as it turns out, light can also curve space-time. It doesn't have to be matter. It doesn't have to have rest mass. So in this case, on the right side, this big fraction is just a constant. We can basically ignore that. This t here represents all of the, what the matter and light looks like. And then this whole right side over here these are curvature tensors, which, if someone is interested and wants to ask, we can talk about those too. But basically, this tells us that matter and light curve space-time. And so then we go to the geodesic equation, and now that we know how it's curved, we can determine how something else, some other matter or some other light, is going to behave inside of that space-time, right? And so this is what we call it looks fancy, and the math tensor math is very unique. And so it can look kind of fancy, but this is essentially just just like any other classical field theory. If you're familiar with electrodynamics, you've got Maxwell's equations, which tell you how, electric charges can create electromagnetic fields. And then we've got the Lorentz force, which tells us how those electromagnetic fields can affect other things, right? So that's sort of how classical field theories work. And in this case, by classical, we mean non-quantum. But essentially, we have objects that affect fields that then affect other objects. That's how a field theory works. And so these are the two basic equations behind general relativity. This is how it functions. And if you know how to do tensor math, you can actually get very specific geometries. You can figure out what the space-time looks like around, at least a small set of objects. And so that's sort of how it works. All right. Another question from the chat says, hey, Nick, do you think we'll figure out dark matter and or dark energy in the next 20 to 40 years? Man, that's a tough question. I mean, I don't necessarily like to... I don't know if... When you make predictions like that about the future, you can end up in a position where you're wrong. And a lot of people that make predictions about the future are wrong. I mean, we've been predicting, nuclear fusion power for a long time. We're like, oh no, 20 years. It'll happen 20 years from now. And then 20 years passes and it doesn't happen. And then, oh no, 20 more years. And so I would like to think that will figure out dark matter and dark energy in the next 20 to 40 years, but it's tough stuff to study. Dark matter is easier because at least we know that it's matter. We have some kind of familiarity with it. We don't necessarily know what kind of matter it is. I'm going to get off the screen share here. All right. We don't necessarily know what kind of matter it is, but we do know that it is matter. It has the behavior of matter that is very consistent with what we see it do. And so that's just a pun here. It's just a matter of figuring out what type of matter it is. And that's the tricky part, but I think that is probably doable in, definitely 40 years, I would think. 20 might be a bit ambitious, but I feel like we could figure out dark matter in 40 years. Dark energy is trickier. Dark energy is a completely different thing. Not only is it not matter, it can't be matter. We only know it's energy. It's an energy term in Einstein's equation. In fact, why don't I screen share this? That happens to be somewhere around here. I'm not sure I have it. There it is. Okay, so this is Einstein's equation with the cosmological constant in it, and this is sort of the foundation of dark energy, right? This term right here, this dark energy term, get that back. This is the cosmological constant, this big lambda right there. And we say it's a constant. Every term in this equation is not an energy. It's an energy density. And so what that means, it's, if we measure energy in, say, joules or something, each term in this equation is a joules per cubic meter. It's an energy density. And so what you end up with is this term at the end that is a constant energy density, which means that as space expands, you end up having to have more and more energy in the space because you have to keep the density the same. If the density didn't, if you didn't create more and more of this stuff, this dark energy, then the density of it would go down, just like the density of matter and the density of light go down as space expands. But according to general relativity, that can't happen with dark energy. And so it's kind of this weird, it has a very weird behavior. It's very alien. It isn't anything that we're familiar with. And so I don't know if we'll figure that one out in 40 years. That's going to be a lot harder. I'd be very excited if we do. It's a big deal for me. I love cosmology, but I don't know if 40 years is ambitious for something we barely understand. Let's see. Someone said, is it true that calculus is what allowed Einstein to come up with the theory of relativity? Well, no, because back in the day when he was doing special relativity, this is before gravity and everything, he didn't even use calculus. It was all algebra and thought experiments. He didn't really need calculus until general relativity, and then plain old calculus just wasn't enough, and he was kind of stuck, and he didn't know what he was doing, and then he talked to a couple of his math professor friends, like Marcel Grossman, I think Marcel is his name, and they sat down with him and discussed it out, talked it out, and then they're like, okay, well, you're going to need differential geometry, and you're going to need tensor analysis. And those are the maths you need to learn. And so he went off and he learned those things. He didn't need to learn that stuff when he was getting his degrees. And so he had to learn that stuff before he could finish general relativity. And I'm sure this is what put David Hilbert at an advantage, because David Hilbert was a mathematician. So he was already familiar with a lot of these things. But it wasn't calculus. It was tensors and differential geometry that made it possible. But it wasn't like he had to wait for that stuff. Though that mathematics had been around for a long time, like at least a century before he was even born. So he just had to find it. Someone had to tell him to use it. Let's see. What else we have here? We have some good questions in the chat. Ricci is coming, guys. Get ready for messy equations. Yeah, that's definitely. I mean, if that someone asks, I'll pull that out. Let's see. Ooh, there's a lot of questions. All right, so let's see here. Your latest gravity video, gravity was caused by the flow of a gradient in time. Yeah, we're going to talk about that. Would dark energy imply that time flows opposite there with that concept? No. Because when you get into dark energy, you're sort of stepping beyond what that video was intended to cover. All right, so a year, 2 years ago, maybe 2 years ago, I put out a video where I said ordinary everyday gravity, the gravity that we experience here on Earth, for example, is caused by what I call the flow gradient in time. And the fact of the matter is that basically everything that ever happens ever in the universe is caused by some kind of gradient. It's always a gradient. And so when it comes to Newton's version of gravity, it was like an energy gradient. You had gravitational potential energy. But general relativity kind of changed all that, and it turned out to be gradients in space-time. But when you're talking about something we call the weak field approximation, which makes it sound like the term weak it might seem a bit subjective, but basically what that means is any field that could be easily explained by Newton's version of gravity. And so that for Earth fits that example. Earth's gravity fits that example. And so in that case, right, if you want to explain a weak field like the one around the Earth, Earth is pretty small and not all that compact. And so it's I should say it's pretty low mass, but not all that compact. And so astronomically speaking, the gravitational field around the Earth is pretty small, pretty weak. But in that case, right, even though Newton's law of gravity works, you want to be able to explain it using the new model, right? Even if the old model works, you want to make sure the new model is at least consistent. And when you do that, if you do that sort of weak gravity, it turns out that the time term, the temporal term, dominates by a landslide, dominates the behavior of what's happening. And so I was able to make a video talking about that and about how the gravity that you experience that, makes things fall to the ground when you drop them, or, you know, you fall to the ground when you skydive out of a plane or whatever, that it has to do with differences in the flow of time at various heights above the Earth, right? And that flow gradient is ultimately still caused by the mass of the Earth. Mass is just confined energy, and energy is what causes that sort of thing. And so, large objects like planets and stars and stuff, just slow down time around them. And gravity is kind of an accidental byproduct of that, right? I see someone asked if gravity was real. Yes. I mean, I suppose it depends on what you mean by real, but it's a real effect. It's a real thing that happens. It just isn't a force in the traditional sense. But what general relativity says is that it says that masses slow down time, and that slowdown in time then causes an effect that we observe as gravity. But the reason I bring this up is because when you talk about things like black holes or neutron stars or the entire field that spans the cosmos, which is where dark energy comes up, you don't have that weak field approximation anymore. You have a strong field, and when you have a strong field, time flow is no longer enough to explain what's happening. You need to include space, because now the space curvature has a significant impact on what's happening, which is not true for the gravity that we personally experience on a daily basis, but it is true in general. So I don't think that you can use that video and then expand on it to talk about dark energy. You've stepped beyond the scope of that analogy. Someone says, can we make matter from energy? No, that's actually a common misconception. Matter, I think the problem is the language, which is honestly what a lot of the issue is. Like, I know that there are some people that don't like some of my general relativity videos, and usually after a conversation, it comes down to language, the definitions of words and how I'm defining them versus how they're defining them. And that is almost always the result of like, well, I'm a science communicator, and so I'm trying to use language that makes sense to, non-scientists, and they're getting on my case for using a different definition of a word that's not very scientific or whatever. And it's going to happen forever. I'm used to it at this point. But the language I'm talking about here is that matter is a real thing, right? We know it's there. It exists. And we know light is a thing, right? Matter and light are things that exist. Energy is just a number. And the same thing with mass. Mass is just a number. Mass is just confined energy. And so energy is just math. It's not real. It's not a real thing that exists. Unfortunately, when people talk about light, they often refer to it as energy, and it causes all sorts of misconceptions. So when they say, oh, well, like when you set off this nuclear explosion or whatever, and energy is released. No, energy is not released. Light is released. And that light has energy. We can assign a number to it that we call energy, but light is released. Real stuff is released. Light and particles of matter and all sorts of stuff, right, is released during nuclear reactions. But you're not creating matter from energy. You're creating matter from light. That is a thing that can happen. You can create light from matter, and you can create matter from light. They're kind of interchangeable. You can transform one into the other. It's just a matter of like an energy transformation. But I would be very careful not to say matter is created from energy, because that's not how it works. You can't create a real thing from math. It doesn't make sense. All right. So let's see here. Whew, it's a lot of questions. Lots of comments on the NASA shirt. It's very comfortable, by the way. Let's see. People asking about good books on relativity. Well, I just posted a video at the beginning of the month about that. You should check it out. Ooh, just reset. Okay. Matter is a form of energy. No. Matter has energy, light has energy. Again, you got to be very careful with the language. We can see the back of our head in the ergosphere of a black hole. All right, so yeah, let's talk about black holes for a little bit. Black holes are always a crowd pleaser, right? Black holes. All right. Black holes are... I have opinions about black holes, if you haven't figured that out from some of my videos. But black holes are sort of the absolute extreme of this effect, right? And so it kind of ends up being weird to think about when you actually get into the math of general relativity, because black holes are something that we call a vacuum solution. And what that means is that the space-time is completely void of matter. And so when we talk about the Schwarzschild, man, I'm not even gonna try and say it. I always mess it up. But there's the original black hole solution to Einstein's equation, and it was the first one. It was the first exact solution, so it's a big deal. But that has to do with the perfectly spherical black holes, the basic ones. Doesn't include rotation. They're a lot more complicated. But when we look at that extreme, there's sort of the extreme version. All the matter that was there has, as far as general relativity is concerned, has collapsed into a singularity. Whether that's actually true is a whole different story, because the word singularity is actually a math term that just means that we broke the model. And so if you break the model, it's kind of hard to argue that it's saying anything about reality, at least in that particular instance. And so you have to be careful. But black holes are definitely a real thing. We have observed many of them. We know that the centers of galaxies have supermassive ones. And we know that, typical galaxies are full of regular-sized ones. They're all over the place. But around a black hole, right, you've got the event horizon, which is the limit of what we can see. And that event horizon is sort of the definition of a black hole. When we say a black hole, we're talking about the event horizon, because we don't actually know what's happening inside. And so when we say the black hole has a diameter of whatever, we're talking about the event horizon. But even more interesting is if you take one of those black holes and you make it spin, weirder stuff happens, right? At that point, what it can do is it can actually drag space-time around with it and create this sort of whirlpool of space-time, which is wild, right? Where it's actually it's physically impossible to sit still. Right? In order to sit still, you would have to travel faster than light, and we can't travel faster than light, so you can't sit still. And so there's this region around the black hole, outside the event horizon, but close, called an ergosphere, and I did a video a few years back on the ergosphere. But basically, inside there, you can't sit still, and you're sort of dragged around as the black hole rotates. But right around there, right around the ergosphere, there's also something called the photon sphere, which is where the curvature is so intense that a photon can orbit the black hole. Right? The curvature is so strong that a path that light takes, which is the straightest possible path anything could take, the curvature is so extreme that the light actually orbits the black hole. And in that particular location, right? How we see things based on light. And so if you had your head at the photon sphere and around a black hole, and you faced like along the orbit, light from the back of your head would, if there was a light to reflect, or a light would reflect off the back of your head, go all the way around the black hole and come into your eyes. And so you'd be able to like see the back of your head in the distance. Oh, man, I'd love to do a video on black hole optics, but I don't have the simulation skills for it. I would need to hire someone to sort of make the geometry environment for me, and I don't know anyone that can do that, so might be a while. But yes, there is a spot where you can look and you can actually see the back of your own head because of the way the light moves around it. It's wild. Lily says, I get that mass affects curvature and that mass is a property of energy, so therefore energy affects curvature, but why does pressure cause curvature? All right, so new screen share. I've got, let's see, where is it? 280. All right. So what I've got here is something we call the stress energy tensor, which looks complicated. It's just a big matrix of numbers. But I'm going to go through and I want to explain what all these terms mean. So this E, this little curly E here, is just the energy density. It's just the amount of energy, whatever energy is confined within the space-time. And then the rest of these diagonals, this P1, P2, and P3, are pressure, which is what Lily's interested in. But we've also got these terms on the top and the side here, which are essentially momentum. So it's about the motion of the matter or light. And then these little sigmas here are shear forces, right? So how parts of the object are shearing against each other. And so in this particular case, right, all of these things contribute to the curvature of space-time, all of them. And as far as pressure goes, if you actually look at the units for pressure, the units for pressure are newtons per, let me get off the screen share. The units for pressure are in newtons per square meter if you do this in standard metric units. But if you multiply the top and the bottom by a meter, what you end up with is joules per cubic meter. And so you can just think about this in terms of thermodynamics, right? When you think about pressure in a gas, what that pressure is telling you, right? We think about that pressure is that, oh, well, that's like the force that it's going to exert on its container per square meter, which is true, but it's also an energy density. It's telling you how much thermodynamic energy is in the system, right? And so where the curly E is just the overall like rest energy of the stuff. You've also got the motional kinetic energy of the stuff, and also its random particle motions within the system, and the shear forces handle like the other interactions and stuff. So like how it's not just about how much stuff is there, it's about how all the stuff, all the particles that make up that object are interacting with each other. All of that is also energy. And so all of that also curves spacetime. And you have to account for that stuff. Usually when we're trying to solve these things, we make approximations and we ignore some of the terms. We plug in zeros for simplicity, but you can't always do that. Sometimes objects rotate and parts of it shear against each other, like stars, right? Something like the sun is going to have a slightly more complicated curvature around it than you might expect because of how the plasma is interacting with itself. So that interaction matters too. Let's see. Can you turn slow mode on so Q&A can be productive because it's too fast? It actually is on. I set the comment speed to 30 seconds so people can't like comment over and over and over again, because the last time I did a public stream, it was crazy. We had almost it was with Physics Girl, and we had almost 1,000 people there, and people were just spamming the chat. And so I decided to turn on the slow mode today, and it's actually been fairly productive. So I am seeing people's comments. Let's see. Someone said, Corey Graham wants to know, I said that YouTuber claimed that the Earth's surface is literally expanding outward. All right. I knew I was going to get questions about this. Okay, so let's just address this. Since I know people are in the chat wondering. There are always going to be people that are going to tell me that I'm wrong about something. And honestly, sometimes I need to be told I'm wrong, because I'm human. I'm wrong sometimes. It happens. I have taken down videos because I have been told I was wrong and I was actually wrong. It happens. But then other times people tell me that I'm wrong and I'm not actually wrong. They're just being extra pedantic about something, or they're what it usually comes down to is this. Let me give you an analogy. So when I make videos, like this video I did with the flow gradient in time was, I think it was a 7-minute, 8-minute video, something like that. I'm not going to be able to cover the whole picture in 7 or 8 minutes. And so what I have to do is I have to choose what part of it I'm showing you, right? So just for an analogy, say the whole picture is a picture of a person. And what I decided to do was I decided to show you something I felt was foundational to the idea, right? Something to get you actually started and get your mind in the right place. And so I showed you a foot, right? I showed you the picture of their shoe. And I think that's okay as long as, you're clear that that's all you're doing, that I'm only showing a picture of a shoe. I'm not showing a whole person. But then people will, they'll get on my case about it, that I didn't show the whole picture, and that's unreasonable. And then I'll see videos. There are whole channels devoted to trying to debunk me, but what ends up happening is sometimes the person has no idea what they're talking about, and other times they know what they're talking about. But what they've done is they've shown you a picture of the hand instead. I showed you the shoe and they're showing you the hand. And they're like, well, this is what general relativity is. And so that person over there that showed you a shoe, that's not human. My hand is human. And that's not good. That's not a good way to do this. And I feel like we need as many people as possible talking about this stuff so that we can reach as many people as possible. And so when I do a video like I did the energy flow in an electric circuit video, and then a few years later, Derek Muller does one. Veritasium puts out a video, and everyone's like, "Oh, he copied you." Well, he didn't copy me. He just covered the same topic, and that's totally fine. That's allowed. And it's important that as many people have the discussion as possible, so it'll work out kinks and it'll be able to reach. I can't possibly reach everyone by myself. It's just not. I don't have the style that reaches everybody, and so I like that other people cover the same topics. But if you're going to sit there and show a different part of a topic and then tell me that I'm wrong because my part isn't real, like, it just doesn't make sense to me. And so there was a video someone posted recently where they explained that one way to look at general relativity is to say that the Earth's surface is accelerating upward toward the object, which, I mean, it's technically true. I've never liked it. It's never really resonated with me. But I mean, if you look at the math, you can technically say that as long as you're defining acceleration very carefully. But just because you can say the ground is accelerating up toward the object, that doesn't mean you can say that the entire Earth's surface is accelerating outward. Because something that's very important for general relativity, and this is what the topic of the live stream is that it's a local model. And what that means is that the math is defined at a point. It is not defined generally, right? You can't look at an equation and be like, oh, well, this is what the geometry looks like everywhere. No, it's what the geometry looks like at whatever point you plug in, right? And so if you've got the Schwarzschild metric, which is something that describes the geometry around spherical objects like black holes or planets or whatever, and what you can do is you can plug in a distance from the center. You plug in an altitude plus the radius of the Earth. And what you'll get is the curvature at that distance from the Earth, that specific spot. And so you can look at the point on the Earth's surface underneath a falling apple, and you can be like, oh, well, it's just as equivalent to say that the point on that Earth surface is accelerating up toward the apple. But you can't say the whole Earth's surface is accelerating outward because the whole Earth's surface is not local. It's a bunch of points that are all accelerating up toward objects, but that doesn't mean that the whole surface is accelerating outward. You have to be very, very careful about that. Now, there is a way to look at it where if you want to try and imagine that like space is falling into an object, you might be able to say that, oh, well, at that point, the surface is accelerating outward, but because space is falling inward at the same rate, the surface doesn't actually go anywhere, even though it's accelerating. And so it's accelerating to stay still, which is even weirder, right? And I just don't feel like, while that's true, I don't feel like people just getting their first introduction to general relativity are ready to be exposed to ideas like that. You're not prepared, right? You're gonna hear a statement like that and be like, oh, well, that's ridiculous. I'm like, and then you'll reject the whole thing, which you have to be ready, right? This is weird, counterintuitive stuff. You need to be ready to hear things. And so there's a specific like educational order to how, and there are stages in your learning process where you're ready to hear things or not ready to hear things. And when that is can depend on the person learning, but you have to be really careful about visuals like that. And so when I'm trying to describe gravity, I prefer to stay in the reference frame of the Earth when I'm talking about objects falling toward the Earth under gravity. Can you switch to the frame of the apple and do things from the perspective of the apple? Sure, but that is not the perspective that anyone doing the experiment is going to have. And so it's going to be a less familiar situation. And if it's less familiar to your instincts, then you're going to make mistakes. And, it's just a fact of humanity, right? If something is beyond, too far beyond your experience, mistakes will be made. And you don't always necessarily know that you're making mistakes. And so you have to be very careful. And so while that explanation isn't wrong, it doesn't really sit well with me for an introduction. All right. Let's see. Thanks for all the super chats, by the way. Jump to this. I sometimes use your videos as a starting point before diving deep into a topic. Yeah, that's how I try to write the videos, and so I'm glad that this is how they're coming across. It says, "Who is the little monster dude on the couch in the back?" This guy right here. That is my pet monster, and I don't mean that like he's a monster and he's my pet. Like that was the name. There was this. Okay, so I'm old as far as the internet is concerned, and so back in the 80s, there was this TV show called My Pet Monster. And it was like a cartoon monster superimposed on like live action people. I think there was a movie or something, maybe two. Anyway, when I was a really little kid, I was super into this. And so, when I was like 3 or 4 years old, I got him as a Christmas present, and, I still have him. He used to have orange, chain handcuffs, which, the family dog ate at one point and chewed up and then buried in the backyard. Didn't find it again until I was 15. And then we were like, redoing the back porch. I was redoing the back porch with my dad. And then all of a sudden, oh, look, it's the handcuffs. But yeah, he's in kind of rough shape, but, one of my most prized possessions. In this stream, you said both energy isn't a thing, it's just math, and that mass is just confined energy. Both true statements, by the way. It says, you owe us a video on the laws of thermodynamics. Oh, yeah. What I really want to do is I want to do some videos on statistical mechanics, or what we say is stat mech in the physics community. But I think that would be fun. And it would explain a lot. I mean, there's a lot of background like that, like thermodynamics, that is super helpful for, later physics like quantum mechanics or general relativity. And so, having a good foundation with that stuff is important. But yeah, so I see Eigen Chris is in the chat. I mentioned his channel in the self-study guide that I put out at the beginning of the month. Definitely check out his stuff. He goes real deep. So be prepared for some math, but it's very thorough. All right. Does the gravitational constant change? No. As far as we can tell, it is in fact constant. Now, this is not a dumb question, right? In fact, in my opinion, there's no such thing as a dumb question. There's only questions asked in bad faith. When you're asking a question, you don't actually want to know the answer. That's not a cool question. But if you're actually interested and you're curious, that's good. And in this case, the fact is there are things that science refers to as constants that aren't necessarily constants, and we're trying to change the names, but tradition is hard. So in the case of cosmology, since that's related to today's topic, we have this thing called the Hubble constant, or at least it used to be called the Hubble constant, which sort of represents the current expansion rate of space. And it's a major part of cosmology and how general relativity applies to it. But it's not really constant. The expansion rate changes over time. And we can map it out. We know exactly how it's changed for the last, 10 billion years or so. Things get a little hazy when we get to the early universe, when we get to like it's called recombination, when the cosmic microwave background was released. Like, that's as far back as we can see. And so when it gets past that, that's when we start to get a little hazy on what we know about the universe. But after that, we got solid data on how space has expanded throughout history. And it turns out that expansion rate changes. The original models, the early models, we assumed it was constant, but it turns out not to be the case. And so we're trying to call it the Hubble parameter now instead of the Hubble constant. But, if you've got old physicists that have been doing this stuff for, 40, 50 years, they're not going to change. They're just going to keep calling it the Hubble constant, and you've got to deal with it. These things take time. But in the case of the gravitational constant, which is that big G I had in Einstein's equation, that appears to be the same everywhere, no matter what. If it turned out to be changing, that would definitely be interesting, but it appears to be constant. Lots of people remembering My Pet Monster. Makes me feel less old. Thank you. Let's see. We can only travel one direction in space. To change that, we need a force, just like traveling through time. For space, we have something to grab onto. Well, I mean, it's not the same thing, though. It's not. Gravity isn't force. It's curvature. But both forces and curvature, like I said at the beginning of the stream, can cause accelerations, can cause changes in direction, or at least apparent changes in direction. Geometrically, it's not a change in direction, which is where the confusion comes from. You can't actually trust your eyes in general relativity. All right, let's see what we got. What do you expect the James Webb Space Telescope to tell us about gravity and space-time, and what should it tell us about the distance ladder? Okay, so we have the opportunity here. This is a big deal. I think with Hubble, the furthest back we were able to look is 8 billion years or so, which, seems like a lot, but the universe is almost 14 billion years old. And so for those who don't know, the farther out we look, the farther back in time we're looking. We're looking at images of the past. And so when we look out 8 billion light years, we're looking 8 billion years into the past. It's really about time. It's not about distance. And so Hubble Hubble was visible light. It saw invisible light. And so we could only go back so far. After that, cosmological redshift is so extreme that visible light has shifted into infrared, and Hubble isn't able to see that. But the James Webb Space Telescope is all about infrared light. And so it has allowed us to see so much further back, like 13 billion years into the past, which is huge. And obviously the data is still coming in and it's all very new. It's only a few months old. But it's either going to confirm what we already know, and any problems we still have, or it's going to give us the data we need to make adjustments to fill in the holes that we have. And that second option is so much more exciting, right? And that's the thing about science, right? It's so exciting to be proven wrong, because the goal is to learn something, right? And if you just keep having confirmations, that's good, but it's not exciting. The idea of being wrong is so exciting to scientists, or at least to science in general, the scientific community. Some scientists might not take it very well, but I think the James Webb Telescope is a huge achievement. It's a big deal, and it's gonna give us so much data. We're gonna be chewing on it for decades. It's a big deal. They say the universe is flat, but it's not all aligned on a table, is it? Okay, so again, this is a language thing. Flat doesn't actually mean flat like a tabletop or a piece of paper. Not in the sense that you're thinking. The universe has a volume. It goes out the same distance in all directions. The observable universe is spherical. It is not a plane. But in fact, we'll pull this up as well. Screen share. We're looking at 328. Okay. Zoom out a little bit. All right. So what we've got here is this is a description of the curvature of space and time overall, like the cosmological size, right? And what really matters here is this K value. This is the curvature value. And try not to get overwhelmed by the whole equation. So the K is what matters. And when it comes to that K, we've got a few options. We've got a closed universe, a flat universe, and an open universe. These are the words we use to describe these things. But what flat means? Flat just means no curvature, right? So if you look at a flat tabletop, it's not curved, right? That's the idea behind it. And so when we look at space and we say that space is not curved, and that is what we see on the grand scale, it turns out that K equals 0 for our universe, as far as we can tell. That means that there's no overall curvature on the cosmic scale. And so we should really say, when we say closed, flat, and open, you should really say positive curvature, 0 curvature, and negative curvature. But that doesn't feel as approachable. And so at some point, someone decided on these basic words, these standard words that everybody uses, closed, open, and flat, to describe what's going on. And it's led people down misconception tracks like this. But the universe goes out in all directions. It is not a flat plane. It is flat in that it is not curved. And so if you were to travel long distances in straight lines, those lines, that line that you took, that you flew on, would stay straight. That's the idea. Your path through the cosmos would not curve. But that doesn't mean we're in a flat plane. So very, very important distinction. Let's see. Lots of things about negative mass in here. That's all speculative, and I try to stay away from speculative stuff. Like, I tried to write a video on tachyons, that's hypothetical particles that travel backward in time. I tried to write a video on it a couple years ago, and I just got angry and quit, because they're so hypothetical. Like, why am I even discussing this? And so I try I try not to cover things that are too speculative or too new. And so there are things that you might see on a channel like PBS Spacetime, great channel by the way, um, that you wouldn't necessarily see on my channel because it's just a personal preference. And so I'll probably never do a video that involves negative mass. Just accept it. Let's see. Do images like the James Webb update our idea of the amount of mass in the universe? They haven't yet. We seem to be expecting. We seem to be seeing exactly what we'd expect. Galaxies. The right number of galaxies in the universe, and having the correct spacing that they should have. But it's not. We have been finding galaxies earlier than we expected, and so the timeline might need to be adjusted, which is a big deal. But as far as the amount of mass, no, that's basically exactly as expected. Let's see. What happens if the James Webb Space Telescope takes photos of clusters that are more than 14 billion light years away, more than the age of the universe? How will the images turn out? They won't. We can't see that far back. We can only see 13.8 billion light years away. Because that's how long ago the first light was emitted. Before that, light was trapped between charged particles, and there was essentially no free light to create images of anything. And so there are no images before that moment. They don't exist. It's just a fact of cosmology. See. Got a lot of questions related to stuff not relativity, so I'm skipping some questions here. Apologize to anyone who's trying to get questions in outside of the main topic. Let's see. Lots of questions. Did the Big Bang happen? Yeah, but I mean, it wasn't an explosion. And this is a common misconception that people have, right? When you actually sit down with the math and you finally understand what's happening, you realize that things are named very poorly. It's particularly in physics, but I think in science in general. And the Big Bang is no exception. The Big Bang was actually coined by one of its greatest detractors, a guy by the name of Fred Hoyle. He was huge in rejecting the entire idea when it first came out. And when that happened, and he didn't even name it on purpose. Usually when things get named and they seem like a really cool, popular name, it wasn't even a scientist. It was a journalist that named it. And so what ended up happening was he was being interviewed, and he was asked a question about the big, he was what they called, cosmological expansion or whatever they called it back then. And he was like, that idea is totally ridiculous. You expect me to believe that the universe started in some kind of Big Bang? And then the journalist published it and the name caught on and it stuck. And so that's why it's called that, but it's not actually an explosion. There wasn't an explosion. There was just a moment in the past when space began to expand. That's it. It wasn't an explosion. Explosions would not be this uniform. It is just space itself was not expanding, potentially, we don't know, but it began expanding, right? And so since we're getting to a point where we accept that we don't necessarily know if there was a time when it wasn't expanding, it might have been expanding forever into the past. Those eternal inflation models, but what we now refer to as the Big Bang is just a time period. It's basically the period in time when our models of physics, our physics in general, became what governed the universe. And so before that time, whatever was happening was not governed by the laws of physics that we know. And that's really all the Big Bang was. It's just the time when our models of physics became relevant. And that was quite a long time ago, and you could easily call that the beginning of the universe, but it's a little more complicated than just an explosion. Let's see. If GR is a local model, how do we use it to model large-scale objects like black holes, galaxies, etc.? Etc.? I would say that wrong. Are shortcuts being used? No. I mean, it's... You can have a local model, an equation that applies to a single point, but write it so generally that applies to each individual point in space, right? So it can, you can have it apply to this specific spot right here, like right in between my fingers, but you could also plug in numbers for this spot, and then it would apply to that spot. You can plug in numbers for this spot, and it would apply to that spot. And so you can do that with any local model, but it's just important to keep in mind that it's not a global description. It's a local description. Once, it applies to an individual point, and that point might be arbitrary. It could be any point, but it is a point. Curvature is a local phenomenon. If you want to talk about global phenomenon, like things that apply to the universe as a whole, then you're not talking about curvature. You're not talking about general relativity. You're talking about topology, which is a whole other discipline of mathematics, which I could honestly do an entire video about. Tommy says, it's not a local model. You got the FLRW metric, which is the metric I was just showing you. That is still local. It's still a local point, right? Each point, you might be modeling the universe in broad strokes, but it's still a point, and if you're looking at a large scale, your point might be like, 10 megaparsecs across, which is like, I don't know, you could say like 50 million light years or something, right? You could say that your point is 50 million light years in diameter, but it's still just a point. It's still local. It's not something that applies to the entire universe. But again, this is a language issue. It's kind of hard to come up with language that describes this. It's so outside of our own experience that we just don't have the words sometimes. And so we're left struggling. Does Hubble's law suggest that space-time itself is made of a near infinite number of expanding spheres? I don't think Hubble's law really implies or suggests anything. Because it can tell us how, space has expanded throughout time, but like it doesn't really say anything about, spherical bubbles all expanding together and into each other. I mean, that is one interpretation, but it is not the only interpretation. And so I don't feel like the math is suggesting anything like that. Could there be no inside of a black hole? Because in order to cross the event horizon, you would have to go greater than c. This is a great question, and this is something I mean, we can't know until we can get at least closer to one, which is dangerous. But I think that, oh, hold on. Just got spam on my chat. All right, so as far as black hole insides go, I think there are a few ways that can go, and we can't know for sure. And so at this point, it's just speculation. And so I would like to just clarify that anything I say over the next couple of minutes is speculation on my part. But it is possible that black holes don't have an inside for multiple reasons. But you kind of have to look at the models, right? Some water here. And so, as far as we can tell, the model works pretty well until you get really, really close, like infinitesimally close to the event horizon. When you start to get that close to the event horizon, things start to get weird. And I don't mean weird. Weird can happen, right? There can be plenty of things that happen in the universe that are outside of our experience. But there are things that it does that just don't actually make sense. And so one of the first things you notice is that different observers can see different things happening around black holes, right? So, in fact, we're going to screen share again. I've got some graphs I can pull up here. So what I have here is a little space-time graph. And this orange thing here is the light cone. It's basically the future and the past. And each of these curves, these green and blue curves, are paths that you can take in space-time. You can see how they're curved because space-time is curved. But one of the things that we notice is that you can see that the paths that are on the outside of the black hole never cross that boundary. They never cross the dashed red line, which is the event horizon. They never cross it. And so if you are an observer that is very, very distant from the black hole, this is what you're going to see. You're going to see things falling in and time slowing down, and things get closer and closer and closer to the event horizon, but they never, ever cross. However, if you are an astronaut and you happen to be falling into this black hole, you're going to see something very different. Your coordinates are going to look something like this. And as you can see, we've got a nice green path here that goes right through the event horizon and straight to the singularity. The hypothetical singularity is over here on the left. And so you could actually, your future is pointed toward the singularity and your past is pointed away. And that sort of gives you an idea of what this hypothetical singularity actually is. But the point is that the distant observer doesn't see you cross the event horizon, but you will see yourself cross the event horizon, or at least you will cross the point that you thought was an event horizon. And so you'll end up seeing something different than the distant observer. And so you have to be that's your sort of your first hint that something is going wrong here, right? There's an event that exists for one person but doesn't exist for another one, and that's kind of a red flag in my opinion. Doesn't necessarily have to be. I could be wrong here, but for me that's a red flag. And then once you cross the event horizon, things just go off the rails. Okay, so then you start ending up with like space and time switching behaviors. And so the inward in that what used to be radially inward is now the future. Right? What has changed? It has changed from space into time. And what used to be time now looks like space. You can actually move back and forth in time. Or at least it kind of, or at least the space is straightforward. That is what it is, right? You can move back and forth, but you're always going forward in time, right? And so that's sort of the behavior, but now you're always going forward in space. And so now that kind of looks like time. It's very difficult to explain. And so that's like red flag number 2, right? Things are getting a little wonky. And then you have to decide, well, now, like, do things go into the singularity? What is the singularity? Why does it exist? Why didn't some other mechanism stop the collapse? And most physicists don't think that the black hole singularity is actually a thing. The term, like I said earlier, the term singularity just means that we broke our model. And so most of us are pretty sure that there's going to be some kind of mechanism that stops the collapse. Now that mechanism could stop the collapse after the event horizon on the inside. So there's still an event horizon. That's a real thing. But then, like, where though, you get a little iffy, right? You got to draw the line somewhere. And I know that there are some models out there using string theory that stop it at the event horizon. Like, the actual event horizon is where all the matter is, and it can't get any deeper than that. It's sort of a 3-dimensional object has sort of essentially been compressed into 2 dimensions on the surface of the event horizon. And so at that point, asking about the inside doesn't make any sense because there is no inside. There's no space-time there. It's just the surface. Space-time is curved so much that a volume has become a surface, which is also, it also feels very extreme, but it is a possibility. And so I think that there are aspects of what general relativity says about black holes that we should be skeptical of until we have a better model that might explain it in a way that doesn't, like, break causality. Because there are even more red flags after that. If you got spinning black holes, you can spiral around what we call a ringularity and travel back in time. And it's just, like I said, it goes off the rails when you get inside that event horizon. And I think those are all indications that we probably shouldn't trust what general relativity says, at least for the inside of the event horizon. And so it is entirely possible that there is no inside. That is 100% a possibility. And I personally like the idea of that, but it doesn't mean that I'm right. Let's see. I already answered that. Let's see. We are black holes. I mean, emotionally, maybe right now, some of us. Let's see. Lots of conversation. Is the universe inside a black hole? I would say no. I've even made a video arguing the no, but I don't think that that's. I mean, if you force it, I think PBS Spacetime did a video on this. If you force it, you can kind of get it to match up, but it doesn't really actually make sense. And so I don't think so. No. Clive recognized my Eddington Finkelstein coordinates for the black hole. Thanks for the observation. Is it fair to say that general relativity describes how energy and momentum curve space-time, but we have no idea why it curves it? Yeah, yes, 100% accurate. And that's the thing with physics models in general, right? We come up, general relativity is kind of our front line for how we explain how gravity works. And the front line model is always the how. That's what models do. They explain how, and they allow us to make predictions. We want to know why, but they never really explain why. And so you can say, okay, well, Newton's model of gravity said, well, gravity's a force and things are, masses are attracted to each other. And then someone says, why? And he's like, well, I don't know. I don't know why. This is just how it happens. And then eventually, Einstein and Hilbert come along and they create general relativity. And general relativity says, well, this is why things fall, right? This is the why. I'm going to answer the why for Newtonian mechanics with a new how. And so now we're left with a new how answer and a why question that we don't have an answer to. And this is the endless chain of discovery, right? We come up with an explanation of how, someone asks why, eventually someone answers that question with a new how, and so on. And the pattern continues forever. And that's not to say that it's pointless, because it's very important that we do this, because the more why questions we manage to answer, the more we understand about the universe. And for me, that's one of the, the crowning achievements of humanity, is being able to understand the universe around us. We can understand the whole universe. We are capable. It just takes time, and we have to do it in little steps. All right. Is gravity three-dimensional? Gravity is four-dimensional. It is for space-time. There are 3 dimensions of space and 1 dimension of time, and it is affected by all of them, right? So when we talk about gravitational waves, we're talking about waves in space and time, which is kind of difficult to wrap your mind around, but it's both space and time count. It's not just space. All right. Well, we're coming up an hour and a half. We should probably call it soon. I was expecting to only take an hour, but gotten some really good questions here. So I'll answer a few more, and then we'll call the stream. Why is an anthropomorphic question? Yeah, so it's more about our desire, right? We like to know why things happen. And it's definitely a driving force for our, scientific discovery. But like the universe doesn't care about why. It just does what it does. Let's see. What we got? How do we know that there is only one dimension of time? Or is it possible that time is multidimensional? I mean, it's possible, but it's possible that there are more than 3 dimensions of space, but they would have to be very confined dimensions. We do have models. We do have hypothetical models, none of which have been verified by experiment, but we do have hypothetical models that have more than one dimension of time. This is a thing that is mathematically possible. The question is whether or not it matches our universe, and we don't know. We can't know that until we do an experiment that shows it. That's why experimental science is so important. Doesn't the increase in space due to the expansion break Newton and dark matter and dark energy break Newton's first law? Well, no. I mean, Newton's first law has basically been updated. I mean, that's essentially what the geodesic equation is if F equals 0. And that's 100% consistent with the updated version of Newton's first law. But I think part of what you might mean is, does it violate the conservation of energy? And the answer is yes. Yes, it does. The conservation of energy principle is not universal. General relativity does break it. The expansion of space creates more and more dark energy over time, and that energy is actual energy that increases. And so that is a violation of conservation of energy, but that's okay. We didn't expect it to hold. And so just no physicist is really all that surprised by that. All right. One more little philosophical question here, and we'll call it. It says, can you help me visualize what the expansion of space would be? I can't wrap my head around it, around emptiness being created or emptiness expanding into nothing. Yeah, nothingness is something that a lot of people have a hard time with. I don't think the human brain is built for that. But I think, and I think that's why it's a lot easier for even for physicists to imagine that the universe is infinite, right? So even though our observable universe only goes out so far, we can only see so far, we imagine that the universe continues, right? We actually know that it continues for a little while, just based on the fact that there's no curvature in the cosmos overall. If the universe was only as big as we can see, there would have to be curvature, and we don't see any curvature. So we know that it's bigger, but we don't know how much bigger. But we do assume that it's infinite for multiple reasons. One is we don't really like the idea of an edge, and so space would have to curve back on itself in order to be finite, and that is not something that makes the human mind very comfortable, right? To have something that doesn't go on forever, but then also doesn't have an edge. And so it's a lot easier just to be like, you know what? Let's just assume it's infinite. It's infinite. It goes on forever. And then we don't have to worry about edges. We don't have to worry about any of that stuff. And so we don't have to worry about the universe expanding into anything because it's just infinity getting bigger. There is nothing on the outside. There's no outside. It's just infinity, and we are just over time getting to a larger and larger amount of infinity. And I think that's about as good as I can do without doing like a whole video on it. But that's my best recommendation for you, is to just pretend like the universe is infinite, just to get you through the day. But on that note, I think I'm going to call it. This has been really exciting. You had a lot of questions. Hopefully I tried to answer what I could. There were definitely some questions in here that I did not have answers for, because frankly, I couldn't possibly know everything. But thank you all for coming. Thank you for all your questions and your participation. This has been really great. And on that note, I guess I'll see you in the comments of my videos. Thanks everybody for coming.